Okay, we're going to continue with some of these product and quotient rules, but we're going to look at some of the more challenging problems now. So we're going to start with number 10, to where we left off on the last video. So in number 10, it looks a little bit more confusing because it has these parentheses, but because we can't actually do anything inside either set of parentheses, the parentheses are actually not doing anything. So we can rewrite it without parentheses and say negative 4, which is really times x to the third, and then that's multiplying 5, and when that x is next to that means times. So really we just have a bunch of things being multiplied here. And hopefully we remember that we can actually multiply in any order that I want. So the x and x, those are like bases, because remember, these exponent shortcuts only work with the same base. So since these bases match, I can put those together. The shortcut is to add the exponent. So 3 plus 6 makes that x to the 9. But the negative 4 and the 5, those are not the same base. So because that's not the same base, one base is negative 4, one base is 5, we cannot use our exponent rules. So instead, we're just going to treat them like regular numbers. So we're just multiplying negative 4 times 5, and like always, negative 4 times 5 is negative 20. Okay, so what we did is, again, because these are not the same base, negative 4 is one base and 5 is the other base, we can't use exponent rules, so instead, we just multiply like normal. Negative 4 times 5 is negative 20. So exponent rules are only for exponents, not for regular numbers. Same is going to be true when we're doing 11 and 12 and we're dividing. So before I start doing my division, I'm going to look at just the numerator by itself on this one. So I'm going to leave everything the same, except I see that in the numerator I have two different m's. So since that base is the same, I can put those together. So let me leave the 12. So now I have m to the 6 and I actually have m to the 1. So because those bases are the same, m to the 6 and m to the 1 makes m to the 7. And then I still have the n to the 8 that hasn't changed yet. And then I haven't done anything with the bottom, so I'm going to leave that alone. Okay. So now that there's nothing else I can do in the numerator, nothing else in the denominator, now I'm going to do this division. And when you divide, so let's look at just a random example over here. Let's just go back to something that we know. We know that 10 divided by 2 is 5. And we write it like this: 10 divided by 2 equals 5. If we really think about it, where is that 5? Is it in the numerator or is it in the denominator? Well, because I can make any number into a fraction, 5 over 1. So actually, when I divide and say 10 divided by 2 is 5, that 5 is actually in the numerator. Even if we don't write it like that, it is in the numerator. So on number 11 here, let's go ahead and take care of this 12. The 12 and the 6, those are regular numbers, but they're not matching bases. One base is 12, one base is 6. So I can't use the exponent rules. So instead, we're just going to divide like normal. 12 divided by 6 is 2. And technically that is in the numerator. And then I have an m and an m. So those do have the same base, so I can use the exponent shortcut. So same base of m, I can take 7 minus 3, and that's going to give me m to the 4. And again, once I do that dividing, that's why we subtract the exponents, because we're dividing, that ends up in the numerator next to the 2. And then we have another like base, n and n, so I can subtract those exponents. 8 minus 2 is 6. And again, after I do all that dividing, this is technically all in the numerator, because I could write it like this, over 1. After you divide, it ends up in the numerator. But because we have nothing in the denominator, I don't actually need that fraction bar there, but just to know that it is actually there. Okay, so let's look at a problem like number 12. This is why it's important to understand that everything once you divide ends up in the numerator. So we have a base of 24. Actually, let's start with this. I have a base of x and a base of x. So I can combine those together. So let's leave the 24 alone for right now. Let's combine these x's. X to the 5th and x to the 2nd is x to the 7th. And then the y we'll just leave alone. So now the numerator is simplified. So now let's simplify the denominator. The only common base down here are the y's. So I'm going to leave the 10. I'm going to leave the x. Y to the, remember there's a hidden 1 here. So y to the 1 times y to the 2nd is going to be y to the 3rd because we're adding those exponents together. So now the denominator is simplified. So we've got this new problem. We've simplified it a little bit. Now I can go ahead and do my division because that's all I have left. So I have a base of 24 and I have a base of 10. So they are not like bases, so I can't use exponent rules. Instead, I'm going to divide like normal. However, unlike 12 divided by 6 being exactly 2, I can't divide 24 by 10 evenly. So I can't just get a decimal number because I don't ever want a decimal, I want a fraction. So instead, I'm going to reduce this number. So how can I reduce 24 and 10? I can divide them both by 2. So 24 divided by 2 is 12. 10 divided by 2 is 5. So unlike number 11 where we didn't have a denominator, I still have a 5 in the denominator. So here's where it's important to understand that when I divide, the number ends up in the numerator. So I have a base of x and a base of x. So I can use my shortcut. 7 minus 2 is x to the 5. Remember, when I divide, it always ends up in the numerator. So I'm going to put that x to the 5th in the numerator. Same thing here, y and y. They have the same base, so I can subtract 3 minus 3. If you see already what it is, you can skip right to that. If not, I'm going to say, well, 3 minus 3 is 0. And it ends up in the numerator, y to the 0. Except we learned that anything to the 0 is always just 1. So then really y to the 0 is just 1. So I really have a times 1 here. But again, if I multiply by 1, so let's say I have 12 times 1. 12 times 1 is just 12. So because it's multiplying by 1, I don't actually need the 1 there because multiplying by 1 won't change my value at all. So then my complete simplified solution is going to be this one here. And for our word problem, Tobias has 2 to the 8 marbles in his collection. Tim has 2 to the 2nd times as many. So something I like to do is simplify my numbers. Let's just pretend that Tobias has 8 marbles and then Tim has 2 times as many. Well, if Tobias has 8 and Tim has 2 times as many, then he would have 16. 8 times 2 is 16. So now I know that I need to multiply. So now we're going to go back to not our pretend numbers, but our actual numbers. And I know I'm going to multiply now, though. So I have 2 to the 8th, and I'm multiplying 2 to the 2nd. And then we can use our exponent rules because we've got the same base, so the base stays 2. But we add the exponents. 8 plus 2 is 10. So how many marbles did Tim have? Tim have 2 to the 10th. Now the point here is just figuring out what operation to do. So we really should solve this 2 to the 10th, use a calculator to figure out what it is. Part B, how many marbles did they have in all? Well, we know that Tim has this much, so 2 to the 10th. We put that in the calculator, we get our number, it's this number here. We know that Tobias had 2 to the 8th, so Tobias has 2 to the 8th, so we're going to put that in the calculator, we get that number here. Well, how do we know how many they had in all? Well, that means I would have to add Tim plus Tobias would give me my total. And I'm not going to take the time to go through that here. I just want to make sure we understand how we could apply these exponent rules to a word problem.